you, Irina. That's a great question, George. And somewhat, actually, that's at the core of what I'm going to try to talk about here. So I gave this, I think it's kind of like a Harry Potter-esque sort of title, Dynamic Organic Reaction Networks and Where to Find Them. It's kind of like magical beasts and how to feed them kind of thing. A bunch of different collaborators here. I highlight Shohei Ohara. I'm going to show quite a bit of his work that he did along with VJ that was actually inspired by some ideas that Harold Morowitz had and are very consistent with what we just heard before. Really pretty cool stuff. So I think, to me, a statement of the obvious is that for life to emerge on this planet, there had to be environments that were capable of continuous synthesis of reactive organic molecules. I think that's probably the simplest requirement. So that's an obvious question. Now, I'll refer to this in a very general sense as dynamic organic reaction networks. I think are self-explanatory when we get to it. What's not at all obvious from a geochemical perspective is how and where could these naturally occur. I think this speaks somewhat to exactly what George was asking. At this stage of what we do, we're generally not worried so much about yield. We're worried about pathway. Can we show pathway connectivity between one state systems to another? But at some point, we do have to worry about yield. And at some point, we have to worry about control functions. And I will point to that. So when one puts together a talk like this, one generally likes to look at sort of big idea papers, and you can't really go wrong, or I think you can't go wrong by looking at big idea papers from Norm Sleep. He always has very interesting perspective. So I hadn't read this particular paper of his, but I did just to kind of get myself energized for putting this talk together. And he says some statements that make me feel really good, like life probably originated here and definitely evolved here. That's a great statement. And if you know Norm, he is very, very careful about what he says. And then I gave him to this line. He said, well, it's probably unproductive to precisely define when autocatalysis became life. And from Norm's perspective, that's an absolutely relevant point, because he's focused on life on Earth and the evolution of both life and the Earth in a interactive sort of way. So he can take that question off the table, but we can't. we really have to address this issue about the broader context of life, how that reflects itself in exoplanets and the possibility of life elsewhere. So again, going back to Norm Sleep's key requirements, he says temperature's key here. We really don't, we've got a narrow band of temperature to play with. It has to be warmer than solid water. So you could have brines that are colder than zero, but at a certain point water is going to solidify, and it has to be probably, he argues, less than 122 degrees centigrade. And then the second requirement is straightforward. There has to be energy. And I like the fact that he said there have always been hydrothermal systems to promote chemical disequilibrium in the Earth throughout Earth history. He also argues that then came phototrophism. I think everybody agree with that. So Norm kind of grounds the questions rather nicely, and both are requirements that seem very reasonable to me. So then I went off and I said, well, at this point, 2018, we must have a pretty clear view of what the Earth's early atmosphere looked like. And I was surprised that the first figure you get when you Google it is this very Harold Urey-ish sort of view of the Earth, even in 2018. So I don't think that that's particularly likely. So another person that's always kind of fun to go visit is Kevin Zonley. And apparently this must have been a really interesting meeting. I think Jack Shostak put it together at Cold Spring Harbor. And what Kevin does, of course, is he takes sort of the same perspective that Norm does, perhaps in a little bit more, if you know Kevin, more Kevin-like way. This very complicated diagram, the bottom line is Kevin would argue that the surface, the Earth itself, became a very clement place for life remarkably quickly. So in this axis of time, he would argue that oceans had completely started to condense at about 1 million years. And at that point, life could go on. He also argues against things like an ammoniated or methanated early atmosphere based on photochemistry. So if you think Kevin Zonley-esque way, you're really talking about CO2. So that gets us to ask about Hadean sources of fuels and oxidants. So we condensed a planet from interstellar material. Of course, one of the most abundant molecules in the universe is hydrogen, but I doubt very severely that any of that hydrogen made its way into the accretion of the Earth. That was left. So we need the Earth to generate the hydrogen that's going to be probably the most dominant fuel. This is a model reaction of sort of pentonization reaction, which is a very efficient hydrogen generator. Mike Russell has considered this for many, many years. Many people do. So it's a very reliable source of a fuel. Maybe there was methane, maybe there was ammonia. Hydrogen sulfide is a good fuel. That would be more of a Urey-esque thing, so we include that. For oxidants, it would appear that CO2 is really the only solid oxidant we have. Things appear to be, Mike could speak to this much more eloquently than I, but sulfate doesn't seem to be reasonable in the beginning. Although I'll talk to you about this and make some arguments that there may have been some other interesting oxidants that we don't normally take into account. So starting with CO2 and hydrogen is a good place to start when considering organosynthesis and life's origins. And so the key is, of course, CO2 reductions, we just heard. Now, thermodynamically, carbon dioxide and hydrogen can do two things. They can do the water-gas shift reaction. It's basically a very fast equilibrium between CO2 and hydrogen, carbon monoxide and water. The problem is almost any temperature, any pressure you can think of, the reaction is always strongly shifts to the CO2 side of things. So it's a fast reaction. It doesn't require a catalyst, but it's not particularly interesting. As the previous speaker noted, carbon monoxide is a great molecule for chemistry. CO2 is not. Now, the methanogenesis reaction is very, very strongly thermodynamically driven at low temperatures. So CO2 plus hydrogen goes to methane and water. So this is a great game, and it's a start, at least. It's not making carbon-carbon bonds, but it's a start for basically building something. However, it's interesting if you go back through the literature, particularly amongst experimental geochemists, they were quickly surprised when they started studying this reaction that they could never see any methane, even though thermodynamically it was the most stable species by far. And they didn't recognize at the time that without a catalyst, you'll form no methane. So you can verify that yourself. And in fact, when you do see methane using gold reactors, where gold is effectively non-catalytic, you'll find that it's due to trace metal contaminants in the gold, because there's always, entropy will never allow you to have pure gold, as pure as you might think it might be. There'll always be a little bit of platinum, iridium, and some kinds of iron. So any methane that you do generate can be attributed. We had a postdoc in my lab who did a very careful experiment showing just that fact, and important but not particularly exciting. So we do the reaction, and this is scaled so that you can see all the products, but you get mostly methane. You get a subordinate amount of ethane, that's the 2. 3 is propane. You get your butane and your pentane and your hexane. So this is fine. I'll talk about the kinetics, but I'll highlight one thing. You do form a bunch of other little molecules, and it turns out these are really going to be the source ultimately of your dynamic organic reaction network. So these are branched and partially unsaturated, but they're very subordinate to the main reduced products. Now, kinetics, this is if theoretically, if you had homogeneous kinetics, you'd predict this sort of behavior or decay of CO2. So we're starting with formic acid, so you only form 25% methane. So CO2 and hydrogen decay exponentially, and then 1 minus exponent production of water and methane is what is expected. But of course, I said you can't do this without a catalyst. So with heterogeneous catalysis, you end up with essentially zeroth order kinetics. So this is what you would predict to see if you did this reaction as a function of time, and that little blue box shows you why you get zeroth order kinetics. In fact, we can show this in a really funny reaction for chemists, because we did a reaction of butane thiol, which is one of the most foul-smelling molecules you could possibly imagine, except for the product of the reaction, which is pentanoic or valeric acid, which is about the most horrendously smelly compound you could. So it's like you just go from bad to colossally worse. But it shows beautiful zeroth order kinetics in its yield. So what we saw in this reaction, this is a funny story to this. So I wasn't particularly interested in this reaction, but I had a summer research intern, and I wanted to give them a shore experiment to do, and I wanted to get them from bothering me. So I thought I could teach them how to weld gold tubes, and I would give them this very simple reaction. I said, just take formic acid, decompose it over iron in gold tubes, and just show me that CO2 is decaying linearly, and hydrogen's decaying linearly, and methane's increasing linearly, and then you'll be done for your summer research. And so he came back in, and he showed me this plot. And I said, that's ridiculous. To go back and do it again, this doesn't make any sense. And so he did it over and over again. So, of course, this is what we predicted. And this is what we see, that in the first couple hours, there's no CO2 at all. CO2 just disappears from the system. Half of the hydrogen you'd expect to see is there, and it just sort of floats there. And then, miraculously, at about 4 to 6 hours, all of a sudden there's an explosion of CO2 and product hydrocarbons. This is the distribution I showed you. So again, it looks very Fischer-Tropsch-like in its distribution. So methane, propane is more abundant over ethane, and so on and so forth, but a decay in the relative yield is a function of chain length. The blue are branched compounds. And when you do a mass balance, you see the carbon budget doesn't make any sense. So for the first 4 hours, 100% of your carbon is just not detectable analytically. It's there, right? It's in a sealed gold tube, but you just can't see it using gas phase analysis at Headspace GC. Similarly, it reappears about 4 hours, but it's now quite subordinate. The black line down below is about the amount of hydrocarbons you would predict you have made, so you're making more hydrocarbons than you had hydrogen to make with. So it tells you that you've got hydrogen generation going on. That's not a surprise. And the hydrogen budget also. And then we did, we looked at stable isotopes. And again, you can see at low times, the CO2, both the CO2 and methane are actually more depleted relative to the starting material, which is the dashed line, which is the carbon in your formate. So that's your missing carbon reservoir somewhere. And the same thing happens over here. The bottom line, what I'm saying is, so then Anurag Sharma was working in our lab, and he's very handy with a hydrothermal diamond anvil cell, which is a beautiful device to allow you to look into the reactor to see what's actually going on. And what you can see is complete mayhem, right? So you're seeing all sorts of different phases here. The absolute opaque phases are your residual iron. There's at least two different liquid, apparently even three different liquid phases that are immiscible. And if you look closely in the Raman spectra, you see abundant transition metal carbonyls. So the bottom line is, in this particular super simple system, organometallic chemistry is very abundant. It highlights the fact that even simple experiments are rarely simple. And the hidden mineral chemistry that drives the system towards very rapid hydrocarbon synthesis. The kinetics are completely unusual. We don't really quite understand them. They're almost explosive. So, you know, I would have thought the system would have established one state or the other. What's special at 4 or 6 hours that causes the system to all of a sudden shift from one state to another is not at all obvious to us. I don't know if it's a profitable thing to really worry about, but it's very reproducible. But either way, I wanted to highlight for this talk that even though we can do very easily all this carbon-carbon bond formation, simple hydrocarbons are not reactive and are not capable of sustaining a dynamic organic reaction network. So even though this is how you have to start the system, the main product distribution is not something that's going to be, in my view, beneficial for an emergent living system, as George talked about this morning and others have talked about. So just this figure is kind of screwed up, but obviously there's a carbon valence state from -4 to +4, and then hydrogen redox over here. And it highlights the fact that if you're just making simple hydrocarbons, as say macromolecules, polyethylenes and alkanes through -4 to -2, or methane thiol, which is a molecule, that's fine, but all of life exists essentially much more at sort of a carbon neutral valence state. And if Art Weber were here, he would go on quite convincingly and I think rightly so, in the benefit of being at around zero valence carbon for the kind of chemistry you want to do. But the bottom line is you see all amino acids are sort of sitting back and forth around the zero valence state, and all the TC intermediates are relatively oxidized. When it comes to organic polymerization, which is something we're always interested in, this becomes critical. So even if you wanted to make a compelling physical argument that polyethylene was your polymer of choice for emergent systems, I don't think anybody would. The problem is that this catalytic chemistry is strongly quenched by the presence of water. And so you're not going to go very far with regards to the activity of water before things fall apart. Now, my colleague Irina, she does some beautiful work with, cyclic drying, heating, wetting, drying, whiting, drying, wetting to do polymerization. But she would also agree at a certain point the activity of water is going to shut things down. Just it's simple thermodynamics, condensation. And that's the beauty, as Art Weber would talk to you about, is the idea of what sugars can do in aldol polymerizations, that they're not condensation polymerizations. And in fact, you can show that sugars will polymerize themselves, albeit into a mess. So there's your messy chemistry. I know you like that. But you can go down to millimolar concentrations and give it enough time, and the stuff will polymerize and precipitate out. I'll show you an example of that. So there's something to be said, is what I'm getting at. Maybe the core of this entire argument is getting a system to sit around sort of equivalently carbon zero valence. So we kind of got re-energized by this. It's a difficult segue to make, but I'm going to do it. Is independent of this, I've been studying the organic matter in carbonaceous chondrite meteorites, and I've been focusing on the insoluble organic matter, and I'm not going to talk about that specifically. But others have predominantly been focusing on small molecules that they can extract. Now, The neat thing about carbonaceous chondrites is they tell you about chemistry in parent body interiors. These are planetesimals that existed for tens to hundreds of millions of years. They had interesting disequilibria systems that were warm but not hot. They were wet but not soaked. They initially start very far from equilibrium, very rich in carbon, predominantly CO2, and perhaps some carbon monoxide, and catalytic phases, iron, nickel, metal, camosite, and troilate, as a iron sulfide, is very, very abundant, relatively speaking, and potentially millions of years of mild hydrothermal reaction and the possibility, perhaps, of chemical evolution. But up to this point, most people have focused on amino acids. There have been detection of nucleobases. There's certainly some interesting chemistry in there. George Koper published a paper in 2011, which astounded me. He is a very careful analyst, and he's been studying the Murchison meteorite, and he detected and unambiguously identified all sorts of interesting compounds that are very familiar to us as metabolic intermediates. And so he finds pyruvate and citrate and alpha-ketoglutarate and so on and so forth, lactic acids over there, alanine, glycolic acid, and so on and so forth. There's even aconitate somewhere here. Down in the corner. But he focuses primarily at doing really precise analytical chemistry and using isotopic analysis to verify the legitimacy of these compounds with respect to their origin. But when it came time to proposing what their formation mechanism was, he said, well, maybe they came from ketene and we get to pyruvate and then we can add potassium cyanide to the system and all this chemistry occur. And, possibly that's okay. But the thing that struck me was if you looked at all these molecules, citric acid, and the previous speaker highlighted an early study I did looking at the hydrothermal decomposition of citric acid, is a fairly tough molecule. You have to go to temperatures on the order of about 200 degrees centigrade to start to see it decompose in a reasonable way. At 100 degrees, I haven't bothered to determine what the half-life is as a function of temperature, but it's a tough molecule. In fact, one of the reasons that people got interested in getting rid of it is it turns out that it's a byproduct of the molasses industry, and we generate more citric acid than we know what to do with. And if you could find an easy way of getting rid of it, this would be a really good thing to do. So it's tough enough that people worry about this toughness. But nevertheless, it will go away. And if you give something like 10 to 100 million years of hydrothermal chemistry at 100 to even maybe 50 to 100 degrees, it's going to decompose. So here's just showing the decomposition at 200 degrees centigrade, and within 2 hours, you drop the concentration of citric acid by 3 orders of magnitude, which tells you, so could something even as robust as citric acid last a million years? Not possible. And that's probably one of the toughest molecules in all the molecules that George Koper detected. So the key here is that none of the molecules that George Koper identified have ever been proposed to form prior to planetesimal accretion. All right, so these things had to form in the parent body due to whatever process was occurring. And he said many of these molecules, if not all of them, are aconitic acid. If you don't freeze it, decomposes on the shelf. Right, so there's no way you're going to have aconitic acid lasting for a couple of days, let alone millions of years in wet water conditions. So these things will not survive. So it would require, in my view, that the only way you could find these things in a meteorite if they were continuously regenerated. And so, in essence, George Koper detected the core evidence we were hoping to find and probably try to do in the laboratory of a natural dynamic organic reaction operating in planetesimal interiors. So it raises the question, how did this start and how did it operate? So the key here is planetesimals accrete from rapid correlation of ice-covered interstellar silicate grains, and the ice is predominantly water, that's why we call it ice, but there's a fair amount of CO2, carbon monoxide, methanol, formaldehyde, my favorite molecule, ammonia, H2S, at all about the same abundance. And then the silicates are anhydrous iron-bearing silicates and amorphous iron-bearing glasses. Radiogenic elements provide the heat, so in the core of a reasonably sized planetesimal, it will get warm enough to melt the ices and start to react the iron to generate hydrogen. So you have an environment that's capable of producing fuels, and it has the oxidants you might like to do. But what also struck me about George Koper's work is that all of these compounds, much like our previous speaker was showing, we've been able to make in our hydrothermal experiments in our laboratory. So every one in blue we made. Now, the pathway, unlike George's pathway coming from this ketene to pyruvate and everywhere else, the pathway we saw it was doing something more like that in terms of connectivity of molecular species. And I highlight the methyl succinic acid there. So this really struck me because these molecules we can make in our little gold reactors, and we see them all the time. However, we had never been able to make fumaric acid, and we never could find a pathway to alpha-ketoglutarate. And so that really intrigued me that clearly this is occurring in Murchison. How come we can't do it? Now, one of the things we've always been focusing on, not worrying at all about yields, but we're just worrying about topology of pathways, is how would you start with CO2 and hydrogen and get to interesting molecules? And so the pathway we like is going, say, through propene to acrylic acid, through a carbonyl addition reaction, and so on and so forth, level by level up. The core to this chemistry, as I'll show you later, is that you can't just do this in a reductive sense. You have to be playing both oxidative and reductive chemistry simultaneously, which is tricky. So, a bit of history. We got involved in this game when Harold Morwitz came to our lab about 20 years ago, and he asked if I could do an experiment adding CO2 to pyruvic acid to make oxaloacetate. And I didn't think that would work at the time, and it didn't. And I thought what happened would be nothing but trouble, and I was right, is that the pyruvate would just react with itself, forming this gooey tar, which is what it does, or it just spontaneously decomposes to acetate, releasing this reductive potential. There are some interesting intermediates, but if you did this reactions as we did them in water, they're very low abundance. But the only product that you do detect that sort of builds up in the system is methyl succinate. So I was really struck when George Koper called that out, because that again looked like a lot of our aldol condensation reactions from pyruvate. And so in any case, but that was as far as we went with the aldol reaction. In fact, I used to say, I know I'm sort of a little jet laggy here, I apologize for this. One of the things I like about this system is the power of the retroaldol component to give you reactive compounds when and possibly you need it. So for example, on the right side, citramalic acid turned out to be the best pyruvic acid generator I've ever seen. And so in terms of high yield, for example, if you have ammonia and pyruvate as its own self-reductant, you can get almost the full yield of alanine 1-to-1 out of citramalate under aquathermolytic conditions. I contrast that with my first and only first author science paper where I made a yield of 0.01% pyruvate over iron monosulfide. And at the time, we were really excited about that. But when you can see what you can do with the retroaldol reaction with something like citramalate, it's just incredible. It's almost 100% of the potential pyruvate generation will give you. And so, in any case, but Harold had been starting to read some interesting papers by, I wouldn't say it wasn't his nemesis, but Leslie Orgel, people laugh, but Leslie Orgel was the chemist, in my view, in this business. And Harold is a biophysicist who was coming into this and just throwing out possible ideas. And I used to drive, I think it's fair to say, Leslie a little bit crazy. And so Harold came to me one time. He said, I just was reading Leslie's book on ligand theory. And he says, it's really very, very good. We should just start working with transition metal cations, which, as you've seen in the previous talk, turned out to be very fortuitous. And so fine. So Shohei Ohara and Vijay, who was a postdoc with Harold at the time, were in my lab, and they just got a bunch of different transition metal chlorides and decided they'd start with. They said, well, we've got to build something from something, so it's going to have to be the aldol condensation. So they started with glyoxylate and pyruvate, moderate conditions, so on and so forth, and some really, really cool pathways emerged. So they found a not particularly high yield, but a very elegant pathway to alpha-ketoglutarate, unambiguously. And due to some other issues, we reran all these experiments. Irina reran all of them to verify that, it wasn't just magic that Shohei and Vijay could do, that is magic that anybody can do. Well, not anybody, but Irina had no problem doing this. They also found a really novel pathway to isocitrate. I was intrigued by the previous talk because we had tried to look at the conversion of citrate to isocitrate. And we could easily get the conversion from isocitrate to citrate, but we could never get around the Markovnikov sort of propensity to put that hydroxyl on that particular carbon. So isocitrate instantaneously goes to citrate. But we couldn't get the slightest amount of isocitrate to form in the opposite direction. But here, you can form isocitrate in a very novel way. So if you take glyoxylate and succinate the way you think it might work, nothing happens. But if you take glyoxylate and alpha-ketoglutarate, you go through this pathway generating CO2 and hydrogen. It was really slick. The yield's not particularly low. Now, if you just start with your product, alpha-ketoglutarate, and in the presence of cobalt, nickel, or zinc cation, you form some succinate through the metal produced, and controllable, so there's two, produced oxidative decarboxylation, glutarate. But if you put iron and copper in the system, you get considerable loss of alpha-ketoglutarate, and you form malate and oxalate and fumarate and ultimately pyruvate, and then a lot of acetate as a product. So some interesting things are going on in the system. As the previous speaker talked, it's almost like a classic Maxwell demon. The frustrating thing about this chemistry is you really, I can't convey. I mean, Eric Smith used to we would sit there and discuss what might be possibly going on at the molecular level, and it's really tricky business. But what it is, tricky or not, is it turns out that these different metals do a lot of interesting different things. I think at the molecular level, what's actually going on is hypercomplex and perhaps unknowable at the core level. But clearly these metal cations are doing some very interesting molecular coordination-based chemistry that enhances certain aldol polymerizations, suppresses other net reactions, minimizes almost no polymerization, and it's clearly, as I would say, a physicochemical reality. It's a very high-loss system, but it's a very dynamic system. And so, for example, you can start with glyoxylate and pyruvate up here. You can wander along. You can get as far as alpha-ketoglutarate. You can go from alpha-ketoglutarate to isocitrate, and so on and so forth. But you can also start to fall backwards through oxidation reactions to fumarate, back to malate, hydration of malate over to oxalacetate, and ultimately decomposition, very rapid decomposition, regenerating pyruvate here and generating or regenerating glyoxylate there. In all cases, acetate becomes your predominant product. So where I'm getting with this is that, as I said in the beginning, it seems like all life chemistry and the interest in chemistry, where you want to go with this, sits at around sort of the zero valence carbon level equivalent. Yet you start out with a system that tends to give you a predominance of methane followed by propane, then ethane, and then so on and so forth, really far away from that. And if everything, this previous talk presented this brilliantly, and it factors into what also Leslie Orgel and Dave Ross were talking about, right? That the idea of if you've got a system that's really great for reductive chemistry, you're going to get stuck. This has always been our concern. And so it really came clear to us, and actually in that 2001 paper, we had identified an area where you had a coupled reduction and then partial oxidation, that you have to have both going on. And the question for us became, how could that be? Particularly in the early Earth, where everybody would presume that things were so reducing. How am I doing time-wise? I'm almost done.
3 minutes, 4 minutes.
Okay, I'm rocketing along, I'm almost done. Well, the simple fact of it is Dionysios Vostouskus, again in our lab, was doing an interesting experiment. And this is a complicated diagram, so I won't waste time with it. But the point is, if you think in equilibrium considerations, and particularly in hydrogen oxidation, then you don't worry things too much. But it turns out hot water, the equilibrium from H2O goes to H2 plus O2 is favored at higher and higher temperatures. And when you start to quench that hot water down, the oxidation kinetics can be pretty sluggish. And so you can have situations where, in fact, hydrogen and oxygen will persist even in a net redox neutral system is what I'm getting at. So ultimately, what we're doing is saying, if you can get a dynamic or a functional dynamic organic reaction network to occur, you can get an awful lot from a little. So this is an example, is just playing around on paper, but if you start with something like butanoic acid and isobutanoic acid, and you allow for these following reactions to occur, and every one of these has been verified, right? So carbonyl insertion, partial oxidation, retroaldol, aldol, amination, reductive amination, you can easily generate over 350 different molecules, starting with saturated and olefinic, including a broad range of things. So the question is, but to get to that, you'd have to have unusual controls. But the bigger problem, and this is the very end of the talk, is the following, is that if you start out with a system and catalyst where you can go from carbon dioxide to hydrogen, most of your products are going to be very reduced, methane and alkanes. You're going to produce a small amount of these potentially reactive molecules that are going to be your dynamic organic reaction network. That system is a very efficient acetate generator, so carbon's just going to flux through there into an acetate, and some of it is going to polymerize. And the bottom line is, and that's going to grow, and that's going to grow, and this is going to stay the same. So everything that you don't want is going to grow, but the dynamic organic reaction network does not. Now, this is just a picture of the polymer that you can make very easily. So what you want to do is you want to find a way of doing this. So one of the things, you want to see a system that can direct catalytically CO2 directly into the dynamic organic reaction network, suppressing methane and alkanes. You'd like to find a way of using your acetate so it isn't constantly being rejected from the system. And you don't mind the organic polymer growing because that might be useful, and you don't mind the dynamic organic reaction network growing because that's what you want. So the question is how in the world to do that. This is where we get into complete fantasy, but perhaps the core to all of this is the idea of start thinking about reactive nanoenvironments. And one of the areas is to actually move your dynamic organic reaction network and your entire system into the organic polymer system. So now you have a system that's generating all of this, and everything is growing. The acetate is following the dynamic organic reaction network. And so the problem is solved if you could do it. So what I'm getting at is that the problem of life's origins is not, in my mind, a chemistry problem. The chemistry is not the problem. We know how to do the chemistry. The question is how to harness that chemistry or to direct that chemistry through some sort of control function. And we'll hear more about that in Christoph Flamm's talk, and this is where I think theory really has to jump into this. So the question is, what is special environment? So key here is we need an environment. The only way you're going to get acetate back in the system is you have to activate it. The simplest way of activating it is through phosphorylation. There's nothing difficult about doing it if you can get the activity of pyrophosphate high enough. How do you do that? You can do that in a nano environment. You can't do that in open water. And the same is true. We have to enhance the control of ammonia activity. And this is, again, if you dilute everything, and George Whiteside's did it critically, nothing's going to happen. So at some level, environments have to develop, and these environments are not living systems, but in my view are systems where you can start to control the activities of things. You have to control oxidative decarboxylation. You don't want to keep throwing away your reduced potential. And you have to control partial oxidation. If you don't have some oxidation, nothing interesting is going to occur. But it has to be balanced with the idea of high loss to the system. So the requirement of a dynamic organic reaction, I think, remains obvious. Precisely where and how it occurs, I don't know. Potential for at least a stable dynamic organic reaction network is, I would argue, probably proven for chondritic environments. So it works. I think that's a remarkable result, and I just got me really excited, re-excited, if you will, about this entire field. So experimental evidence supports the potential chemical topology that would do this, but both redox and oxidative chemistry have to operate simultaneously. This is not classically the kind of chemistry that you might think about doing in the laboratory, but it may be that we have to start thinking about that. Perhaps chemistry along gradients and so on and so forth. True lab demonstration of a dynamic organic reaction network, I would say, remains elusive, but we saw snapshots of pictures and pieces of what can be done. But setting up a system that actually would grow would be the de facto. It's not a criteria for life, but it is a criteria that I would say would be very, very interesting to see. And that's all I have to say on that topic. Got a little jet laggy there. Eric.
Thank you, George. So, questions?
You want the blue box?
Sorry to do this twice, but I want to ask about a general theme, because this morning in George Whiteside's talk, one of the conceptual pillars he brought up was the essential role of kinetic traps. And in biochemistry, that's clear. This is a thing Everett has emphasized in geochemical contexts for, forever. Yeah. Apologies. But it's been hard to get at systematically. So if I look at what Joseph showed by controlling for the fact that when you scrub, you can find these complexity-generating intermediates, but if you put them into the solution, you get nothing. And then your black hole for carbon, which then suddenly comes up.
Right.
I think, okay, it looks like we have surface-associated traps. We have something that has a time lag. It's in a transition from being a metal to being an oxide. And it's in that intermediate state. Its band structure is changing, its site density on the surface is changing, possibly its morphology is changing, and we have overwhelming evidence that it's a kinetic trap that's crucial to the distinction between going into one of these dead ends and going into complexity. How do we study that systematically?
That is the grand challenge, because what we want to see, so getting back to the idea of this being a constraint at all, and I think in some ways the best we can hope for right now, I was talking to George this morning, the nice thing about this field is it's so wide open, and it's so wide open because we're so colossally ignorant. We have difficulties. I think George has talked this morning, perfect. We can't even really clarify what we think is life, what is semi-life, what is dead, and what is semi-dead. So we, at least I feel that we can try to place some emphasis on constraints, and that's where the geochemistry becomes so critical, because it evidently occurred on this planet, subject to the laws of chemistry as defined by this planet. At the same token, there's a lot that has to happen. So, for example, this explosive effect that you saw in this one so-called simple experiment, I showed that as a demonstration of that simple experiments aren't simple. But I also had to say that if that was a useful state, then you'd have to say on this planet it would have to be a continuously regenerating state. So this has always been the problem. Whatever one experiment we set up is set up, in a sense, intrinsically thermodynamically to move in the direction thermodynamics require it to go, and it goes as far as the energy available to it does, and then it stops. But we know that that's not sufficient to get us to where we need to go. I don't know if I'm articulating this as well. So that's why I got so interested about George Cooper's results, because clearly in this planetesimal, somehow this system was able to make pyruvate, it went away, makes it again, it goes away, make aconate, and it makes it enough so finally when the system freezes out, it's able to freeze out at least some signature that those molecules were being regenerated over millions of years. So constantly I'm trying to think about what's the experiment. And getting back to what George was asking, if you could do the experiment, you could start to show the components of the network growing in, perhaps through cycles that you could develop. And this is where Christoph Flamm's approach is critical here. I don't know yet how I want to control the system and whether, so he might look at this network idea and start to say, as you said, knobs and buttons and things like this, that's okay, and start playing around with them. And then can you find a geochemical set of conditions that allow you to tweak the knobs in a way that makes sense, such that the chemical system you're interested in grows as opposed to decays. And what I tried to show you was, we see the topology of this network growing, it's a lossy system, right? And most of the stuff is going to acetate so fast to make your head spin. So nothing that we've done in the laboratory shows us anything other than the connectivity of molecular states. And we have to go to that next level of playing around with the knobs in a dynamical system and then seeing, does that take us off the table or keep us on the table?
You mentioned dawn has been proven for quadratic planetesimals.
To me, it has.
Yeah, I believe that. But I also want to point out, dawn may also be proven for this small moon of Saturn, this Enceladus, because from the plume we can measure this array of organics, which are obviously being manufactured from inside, and they have been preserved certainly over a long period of times, like millions of years.
Yes, I agree with you. Actually, Enceladus is becoming one of the more interesting objects in our solar system, and I hope we study it much more closely. Yes?
A question that comes up listening to the several fascinating last talks and listening to my colleagues, I form no judgments publicly at least, is that the kind of chemistry that you do is, CO, hydrogen, high temperature, hydroformylation, that kind of thing. And what many of my colleagues think is that it's all done in space. It's HCN and CO and stuff that forms there, and particularly HCN, maybe acetylene and cyanoacetylene, so that you've done all the reactivation chemistry there.
Right.
And so there's that approach. There's also the approach that says, why work with CO2, which is a horrible reaction for anything except nucleophiles? Work with CS2, because there's an enormous amount of CS2 around. And there's H2S, and there's a lot of H2S, and that's a great nucleophile and an activating agent. Do you consider these as independent themes, or is one going to turn out to be better than the others?
Well, that's an excellent question. So HCN is a fantastic molecule to do chemistry with, and I don't have anything against it personally, but you're laughing. I heard that. but it does have a problem, which is it hydrolyzes really quickly. So I recall when people were worried about terrorist threats and things like this, and I knew Quabbin Reservoir really well, and people said, well, oh my God, what if somebody sneaks up one night and they dump, tons of potassium cyanide in Quabbin Reservoir? And people were like, well, we'll have a lot of formate then, because it hydrolyzes so quickly. So in my view, and this is partly my bias in terms of trying to place constraints on my own set of questions, for you to get to the point where you have a dynamic organic reaction network in a carbonaceous chondrite, whatever hydrogen cyanide might have done for you in the very beginning has been overprinted by millions of years of hydrothermal recurrence. So unless you have a mechanism in the interior of the planet to regenerate some of these interstellar molecules, I would take a lot of them off the table. I love carbon disulfide, but it also is very strongly prone to hydrolysis to CO2 ultimately. It's a great molecule. I remember Leslie Orgel, I was sitting in a meeting, he was getting really, really excited, and he kept asking me, have you ever worked with carbonyl sulfide? And it turns out it became a wonderful polymerization reagent for amino acids with a work that he did with Reza Ghadir. So these are great molecules, but I fear that, so I alluded to this. So there's a big problem with ammonia. And the problem is the following. If you allow me all the ammonia or ammonia equivalent that I could have, then making things like nucleobases is very, very easy to do. And I can do them in the laboratory. I like urea, which is equivalently ammonia, plus CO2. But the biggest race I have when I do this, for example, making uracil, very easy to do. The yields are really low. The only reason the yields are low is because I'm competing with hydrolysis urea as fast as I'm making the uracil. It hydrolyzes so quickly. If I could crank that up, so I don't know how to deal with that. So it's getting back to your question, it's really interesting. I think I don't have to worry about HCN. I think I don't have to worry about carbonyl sulfide. I know I have to worry about ammonia. There just doesn't seem to be an easy way of generating enough ammonia or keeping the activity high enough. And this, again, I think factors into the idea that one has to have some sort of nano environment where you can enhance the effective molarity of ammonia way higher than perhaps the ambient would be. And I like the idea of polyelectrolyte gels or polyelectrolyte polymers that might actually enhance the molar concentration of ammonia, even if it's in equilibrium with less concentration of ammonium in a solution it's in equilibrium with. It's like effective molarity with proteins.
Maybe similar question. So, thank you for the very interesting alpha-ketoglutarate synthesis reaction. My question is that if the glyoxylate is replaced with formaldehyde, so formaldehyde and pyruvate reaction, what happens? So this is why probably the formaldehyde would be much more abundant in solar system compared with glyoxylate, right?
With you mean glycol? So formaldehyde is very abundant molecule. It's like
yes.
one formaldehyde per 100
yes.
waters.
Yes.
But what's the other?
Formaldehyde and pyruvate.
Oh, yeah. Formaldehyde pyruvate versus glyoxylate pyruvate.
Yes.
You're saying.
Yes.
The problem with formaldehyde is it's a great molecule too. So that's where, getting back to George's question, formaldehyde is stable enough that it can hang around and polymerize. Now, usually, there are great stories in all these things. I remember the first time I was trying to do formaldehyde polymerization, and it just never worked. And I was on a train with Leslie Orgel, and I asked him, why doesn't this work? And he said, it's because you're doing it right. He said, if you do it right, it doesn't work. But he said, the trick to making it polymerize is you give it some glycolaldehyde, and then the thing takes off very autocatalytically. And so the trick is, I'd say, fortunately, we can say there's glycolaldehyde in these interstellar ices as well. It turns out, and this I'm not going to divulge, I'm very bad at showing data before I publish it, so I'm not going to mention it. But we have found a way of making formaldehyde polymerize with itself without giving it glycolaldehyde. This is really cool, and I'm not going to say a word about it. But it's interesting. But the formaldehyde will eventually, through the Kanazawa reaction decompose. So what limits the yield of polymer that you ultimately get from formaldehyde anyway is the fact that it will decompose to formic acid and methanol. And that's an irreversible thing. Formaldehyde's a great molecule. I like it because I don't think that no one has ever advocated that you could make it hydrothermally. It sits on the very, very top of an energetic mountain. So there's only two ways to know that we make it. You either do it with, photochemistry, or you do it with interstellar ices, and again, photochemistry, or high molecule reactions. So it is sort of the one thing that's interstellar, I believe.
So, George, thank you. I want to go back to your comment about ammonium. So how did we make ammonium? So you started off your talk with a discussion of early Earth's atmosphere, and we haven't changed much since Urey, but I think that's not true.
Yeah, I agree.
I mean, Urey advocated for a reducing atmosphere.
That's right. But I think now we think it's more oxidized.
More oxidized. So you had another oxidant. You had N2 gas.
That's right.
And we don't treat it as an oxidant. We almost ignore it.
That's right.
And so why is it that we get ammonia at standard pressure, and in fact it was 0.8 bar, probably even lower pressure, and we don't get it from hydrothermal vents?
Nope.
So how do we make ammonia on the planet before life?
That is very much, in my view, an elephant. Mike does. So the simplest way to do it, that I could, if you said, George, I'm holding a gun to you, what I would say simply is,
he wants nitrate.
So nitrate is the easiest way to do it. And the easiest way to get nitrate is through photochemistry with water and dinitrogen in the upper atmosphere, and you rain it out. Then you can make very high quantitative yields. If you take that off the table, I think you've got a real problem. So I don't want to strongly put myself into what the source is, but I'm strongly advocating that we have, I believe, a nitrogen problem that has to be solved. And currently on Earth, we have a nitrogen problem because we are using, we're using more ammonia than we can actually fix through nitrogenase. So it's a problem now, and it was a bigger problem then. And
so I went through this calculation with Canfield a few years ago in a paper in Science, and if we appeal to nitrate as a source without molecular oxygen on the planet, so we're doing it with lightning, right? You will get approximately 10 to the minus 10th molar concentration. 10 to the minus 10th. This is, you're sub-nanomolar.
Oh, yeah.
It's really, really, really low.
It's a huge, so that's why I was saying that, again, I think we all know this intellectually, this idea of, I think John Barrows coined it initially, the 1 kilometer cell, the idea that life as a system could ever have been occurring in a dilute ocean is impossible. So one has to say, okay, even that tiny amount of ammonium, if you could find a physical chemical mechanism by which you could concentrate it in a way that doesn't violate the laws of physics, and particularly the laws of entropy, the best way I can think of doing that is through osmotic interactions. That, for example, I did my thesis in coal chemistry, strangely enough, and one of the things I do is I would osmotically dilate coals to measure viscoelastic properties. And what happens there is that you achieve a thermodynamic equilibrium where the molarity of your compounds can be very high inside this gel relative to their concentration in a medium, say, outside. So it was kind of where I was leading people. I think that you have to be able to create microenvironments that at least locally take a small amount of ammonia and enhance that to the point where you can start to, because the way I look at it is in a living system, right? So, for example, ATP synthesis, from a living system point of view, is just a mechanical way of locally getting the concentration of phosphate so high that making the phosphate diester bond is costs you nothing. Right, but then you send it off to a system where all of a sudden that's not the case, and now you got a really energetic molecule.
So, but let's talk about it in the stepping stones. I'm sorry, but the stepping stones, we're missing one of those big stones.
I agree. I completely agree. It's a huge problem.
Yeah, I hate to be the one to interrupt all this fascinating debate, but we do need to move on.